Now, today we start on important topics. We first talk about right here. Let H.V. Hilbert Space. H.V. Hilbert Space. Then, what we talk now? H.V. Hilbert Space, and A belongs to a dual of H. Then, there exists unique element UF belongs to unique element UF belongs to H such that Fx equal to x UF for all x belongs to this H. Okay, then how we prove it? How we prove it? This write as some theorem. Okay, write this theorem. This one is the test statement of this theorem. Let H be Hilbert space. F belongs to dual of H. Then there exists a unique element UF belongs to H such that Fx equal to this. How we handle this one? First we define here. We define is dual of H to H by this F equal to UF for all F belongs to H star, where Fx equal to x UF. Okay, for all x belongs to H. Now we mark test one. What we see now? We see what? Let Fz belongs to H dual of H star will denote. Then S of F plus G equal to how much? U of F plus G. Okay. Now we know about that F plus G equal to F plus Gx equal to X U F plus G. Okay. Then here Fx plus Gx equal to how much? Fx plus Gx equal to X UF plus X Ug. Okay. Then how we handle it? We know about that F plus Gx equal to Fx plus Gx. Okay, and this implies x UF plus G equal to x UF x Ug. Okay, this equal to x UF plus Ug. This implies that what? This implies that, so here we write UF plus C equal to UF plus UC. Okay, now we erase this portion and obviously do second part. That means here we'll see about that UF plus G equal to UF plus FC. Okay, second part, let alpha belongs to K. Then what we see here, F belongs to dual of H and X belongs to H. Then S of alpha F equal to U of alpha F equal to alpha closure UF equal to alpha closure SF. Okay, then now we write here alpha of fx equal to alpha f of x equal to alpha of x uf equal to x alpha closure uf. Now we write here x u of alpha f equal to x alpha closure u of f. So this implies that u of alpha f equal to alpha closure u of f. So S is not homogeneous. We write here S is not homogeneous. Now S is a conjugate linear operator. So S is a conjugate linear operator. S is a conjugate linear operator. Okay. Now we also here we done this. If S is not homogeneous, then S is conjugate linear operator, and obviously H be Hilbert space, and then there exists a unique element fx represented by this. Okay. Now we erase this portion and going to further discussion about one theorem. Now this theorem is, we write the statement of this theorem here. Okay, let C be a subset. Let C be a subset of a normed space X, of a normed space X over K. Okay, then the following are equivalent. Then the following are equivalent. First, C is bounded on X. Second, FC is bounded in K. For each F belongs to X. Now implies A implies B. Suppose that C is bounded. Suppose that C is bounded. Then there exists R greater than 0 such that norm of X less than R for all X belongs to C. Let F belongs to X star. Then if X less than equal to norm of X less than R norm of X for all X belongs to C. Hence FC be bounded. Okay, so what we see about that, if C is bounded, then this one happens, mod x less than r, and then obviously mod of fx also bounded for all x belongs to C, hence fc is bounded. Okay, now we write here b implies a. Okay, then what happened here, we write suppose that fc is bounded, fc is bounded for each f belongs to x dual. Let x belongs to x12. Define fx x12 to k y f of xj equal to j of x for all j belongs to x dual. Clearly f of xj be linear. Note that f of xj equal to j of x less than equal to norm of j norm of x for all j belongs to x dual. Okay, then hence fx belongs to b of x12k. That means with norm of fx less than equal to norm of x. Okay, marked as 1. Next we discuss about another portion. This portion is we write in simple way, since x is an element, since x is an element of Banach space x, of Banach space x by Hahn-Banach theorem, by Hahn-Banach theorem, there exists bounded linear functional, there exists bounded linear functional from x onto k, from x onto k, such that j0 of x equal to norm of x and norm of j0 equal to 1. Okay, then what would happen, we erase this portion. For all j belongs to x, Then in particular norm of x equal to this one j0 x equal to fx j0 less than equal to norm of fx. Okay, since j0 equal to 1 equal to here write j0 and then this one equal to norm of fx. Okay, marked as this one 2. So hence from 1 and 2 we get, hence from 1 and 2 we get norm of fx equal to norm of x. Okay, then what happened next time? By assumption fxj x belongs to c equal to jx x belongs to c equal to jc is bounded for each j belongs to x, dual of x. Okay, so by assumption fxjx belongs to c equal to jc is obviously bounded for each j belongs to x dual. Then uniform bounded principle, by uniform bounded principle we conclude that if x belongs to c, subset of bx star k is uniformly bounded, okay, it means that this one norm of fx x belongs to c is bounded. This implies that norm of x belongs to c is bounded. This implies that c is bounded. Okay, then what happened? Let C be a subset of a normed space X, then the following are equivalent. C is bounded on X, and this implies FC is bounded in K. And obviously FC is bounded in K. This implies C is bounded. Okay, we now prove these portions, or we are seeing that this one is easily done. Okay, so all are understand this problem, I think. Now we erase this portion and going to further discussion about another theorem. It is important for us. Okay, theorem. Write this theorem now. Let Y be a closed subspace of a Hilbert space. Alright, let Y be a closed subspace of a Hilbert space X, and if y to k be a bounded linear functional, linear functional, then there exists a unique bounded linear functional if delta x to k such that if delta x equal to fx for all x belongs to y, and norm of f delta equal to norm of f. Okay, then now we have to prove this theorem. We write the statement: let Y be a closed subspace of a Hilbert space, and if Y to K be a bounded linear functional, then there exists a unique bounded linear functional f delta such that this one we have to prove now. Okay, so how we prove this? We write here proof. Start now by Hahn-Banach theorem. There exists a bounded linear functional. If delta x to k such that if delta x equal to fx for all x belongs to y, and norm of f delta equal to norm of f. Okay, now let g x to k be a bounded linear functional such that gx equal to fx for all x belongs to y, and norm of c equal to norm of a. Okay, then Weier's representation theorem, there exists uv belongs to x, such that if delta x equal to xu for all x belongs to x, and norm of f delta equal to norm of u equal to norm of f. Okay, and obviously g delta x equal to, and g tilde x equal to xp for all x belongs to x, and norm of g tilde equal to norm of g equal to norm of f. Okay, so now we're going to define another function. It is our portions also. Okay, then define here, define age x to k y hx equal to x m plus v by 2 for all x belongs to x. Now here hx equal to half of xu plus half of xp equal to f tilde x plus g tilde x by 2. Okay, then what we define here, or g tilde, or here write gx, g tilde gx, here we denote gx, so dgx is better. Okay, not g tilde gx. Then what happened, then happened that this one equal to fx and gx, f tilde x and gx equal to 2fx by 2 equal to fx for all x belongs to x. Then what happened, then note that age belongs to bxk. Okay, with same thing, norm of age equal to norm of u plus v by 2. Thus h is also a continuous extension of f. Thus h is also a continuous extension of f on whole space x, on whole space x. Now note that norm of f less than equal to norm of h equal to norm of u plus v by 2 less than equal to half of norm of u norm of v equal to norm of f. Thus norm of f equal to norm of u plus v by 2. Now by parallelogram law, norm of u plus v whole square plus norm of u minus v whole square equal to 2 norm of u square norm of v square. This implies that 4 of norm of u square plus norm of u minus v square equal to 4 of norm of v square. This implies that norm of u difference v square equal to 0, this implies u equal to v. Therefore what we get that f delta equal to z. Therefore f delta equal to z. So we find what? We find a unique bounded linear functional f delta. Okay. So what we discuss today? First we discuss, obviously if H be Hilbert space, then F belongs to dual of H. Then there exists unique element UF belongs to H such that Fx is represented by inner product of an element of H and an element, that means two element of H represented Fx. Okay. Then next what we done here, we see that S is obviously a conjugate linear operator. We didn't define S, and this one is conjugate linear operator, not U. Then next we see that C be a subset of a normed space X. Then the following are equivalent. That means C is a bounded on X, then FC is bounded in K for each F belongs to X. Okay, we also see this proof of that theorem. Next we discuss about that if some closed subspace of a Hilbert space, then a bounded linear functional have, and obviously we get a unique bounded linear extensional functional, okay, which satisfies, that means those properties of f delta x equal to fx for all x belongs to this subspace, and norm of f delta equal to norm of f. We also discussed these three theorems, and today we stop here.